In this video, we're given the graph of a rational function, and our goal is to find the equation of that function that's going to produce this graph. So we're going to break this down, and we're going to look at the numerator, what contributes to factors there, and then the denominator as well. We'll also go ahead and find the slant asymptote that goes with this. So first of all, the numerator. What that has to do with is roots, or zeros, or x-intercepts. So that's where our graph crosses the x-axis, or touches the x-axis. So a little zooming in here. It looks like we have two x-intercepts, or roots or zeros. This one is at -4, and then we go 0, 1, 2 going on the right-hand side. So it looks like -4 and 1 are going to be what we would classify as our roots or zeros. Next, let's go ahead and pick out what factors go along with those. So what we always have is it's always x minus whatever the root or zero is. So for the -4 case, we have x minus a -4, which makes x plus 4. And for the 1, we get x minus 1. All right, the next thing to think about is what will the multiplicity be for each one of these? Okay, we can determine that based on whether we touch the x-axis at each one of these x-intercepts, or if we cross the at an x-intercept. So at the -4, hopefully we notice here, we start above and we cross over the x-axis. So what that tells us is this is going to be an odd multiplicity. All right, the same thing is true over on the right-hand side at the 1. We start above the x-axis and we go to the opposite side. That means this is also going to be odd. Now, if we had come down, touched, and come back the same direction, that would mean it was going to be an even multiplicity. But that didn't happen in our case. So typically what we want to do, unless it's pretty obvious that it really hugs into the x-axis more on one than another, we're just going to use the smallest odd multiplicity. All right, so let's go with 1 for each one of these. We're going to kind of build this up over on the right-hand side. So our numerator is going to be x plus 4 times x minus 1, both raised to the first power. All right, next, our denominator. The denominator is found by looking for vertical asymptotes. So back to our graph here, it looks like we do have one vertical asymptote indicated. It's going to be right here going up and down with the dashed line, and that's going to be at -2. It's a little bit difficult to see, but right here at the -2, that's going to produce a vertical asymptote. So that vertical asymptote's at -2, and very, very similarly to what we did with factors in the numerator, it's always x minus whatever the vertical asymptote value is. So it's going to be x minus a -2. We'll make it an x plus 2 as a factor in our denominator. And then finally, the multiplicity question, like what exponent should this factor be raised to? So where we determine that from is these tails as we get close on the left-hand side and on the right-hand side, because those are going opposite directions, because one's going down and one's going up as we get in close to that vertical asymptote. They're on opposite sides, very similar to how we crossed over the x-axis for our zeros or x-intercepts. You can think about it the same way, that this is going to be an odd multiplicity. All right, so again, in this case, we want to think odd multiplicity will probably just go as 1 for our exponent there. We don't really have to put 1 in there. One last thing, we want to make sure that we get exactly this graph. So we need to identify one additional point and put a scalar multiple out in front, such as an a is typically used in this case. So looking at our graph, one additional point that I notice is, and it's oftentimes easiest to pick out, is the y-intercept. So this value on the y-axis is going to correspond with, it looks like the ordered pair is 0 left or right, up 1, so 0, 1. All right, so that's going to be an x value and an f of x or y value going on there. So we're going to take those values, go over to our function, and fill in for f of x with 1. Still have our a here. And then 0 goes in for each of our x's. little bit of simplifying. We only have one number going on, or we have a bunch of numbers and just a. So let's go ahead and solve this down for a. So we have 1 equals a multiplied by 4 times -1 over 2, which is going to work out to be 1 equals a times -4 over 2. So 1 is -2 times a, and to get a, we'll just divide both sides by -2. So -1/2 is our value for a. Putting that back into our function, I'm going to go ahead and replace the a that was out in front with a -1/2. So we still have x plus 4, x minus 1 in our numerator, all over x plus 2. Now at this point, if we were just asked to find the function itself, we'd be done. All right, and you could put a negative out in front, a 1 in the numerator, a 2 multiplied by the entire denominator if you wanted to. So just rewriting this real quickly for you, it could be x plus 4, it could be x minus 1. That 1 could be in our numerator. You don't have to write it there. We could have a 2 in our denominator multiplied by the x plus 2. But I'm going to leave that -1/2 up in the numerator. And the reason why I'm going to do that is I want to find the slant asymptote. So the slant, or another way to say that, is oblique asymptote. And really what that boils down to is we're going to have to divide the top polynomial by the bottom polynomial. But this is going to be easiest to do if we use synthetic division. So what I mean by that is I'm going to go ahead and expand out our numerator. So I have my -1/2. And then I'm going to go first, outer, inner, last, and go x times x makes x squared. X times -1 makes -x. +4 times x is +4x. And then +4 times -1 is going to be -4. That's still divided by the x plus 2. So I'm bringing that along. All right, combine a few like terms. -1/2 comes along. X squared plus 3x minus 4 all over x plus 2. All right, and then what I'm going to do now is distribute that -1/2. So we're going to go -1/2 times the x squared. -1/2 times the 3x is going to be -3/2 x. And -1/2 times -4 is going to be +2. All over x plus 2. All right, we've got some fractions we have to deal with, but we're going to make this work. All right, how we're going to make it work is because we're dividing by a polynomial that is 1x to the first power, we can use synthetic division to speed this up. We could always use long division, but let's use synthetic division. So how that's going to work is, because we're dividing by x plus 2, -2 is going to go out in front here, and then we're going to take each one of these coefficients from the top polynomial, -1/2, -3/2, and +2. We didn't skip over any powers of x, so we don't need any placeholders there. I'm going to leave a blank row going on here, and we'll execute the synthetic division. So the first value comes down, -1/2 comes down. For synthetic division, remember it always goes multiply, and then you add. Multiply, add, multiply, add. We're always going to be multiplying by that -2, the value out in front. So -2 times -1/2 is going to give us +1. And then we add vertically. So that adding vertically, we're going to go -3/2 plus 1 gets us to -1/2. Then we multiply again, right? -2, the red value out in front, times -1/2, again gives us +1. And then we're going to add vertically. We get 2 plus 1 makes 3. All right, what we need is we need the quotient to go along with this. So remember, the remainder is going to be this last value. That's the remainder, but the quotient will be, this is going to be a constant, and this is going to be x to the first power. It's going to be -1/2 x minus 1/2. All right, so you may be saying to yourself, all right, we found the oblique asymptote or the slant asymptote, we can actually put that in the graph. So we have negative 1/2 x minus 1/2. We ignore the remainder with that. So y equals negative 1/2 x minus 1/2. Just copying that down. That's going to be the equation of a line. And if I want to graph that equation of a line, what we want to do is we want to probably start with the y-intercept. Right? Remember this was 1, so it's going to be at 1/2. Sorry, negative 1/2. Making my mistakes here. So negative 1/2 is going to be down here. For its y-intercept, that's given by this value here. All right, thinking mx plus b. Then our slope, m, is going to be also negative 1/2. So I'm going to visualize that initially as negative 1 over 2. Remember, rise over run as we're trying to find additional points. So I'm going to think of that as going down 1 and to the right 2 to find additional points. So you can do this down 1, right 2. There's an additional point. I'm going to get rid of these. And I'm just going to make this a counting problem. Down 1, right 2, down 1, right 2, down 1, right 2. And I realize that I'm going with 1/2 increments because of our units on this, but it's just based on how our grid system's looking. All right, the other way to think this through is you can reverse these directions. You can think positive 1 over negative 2 by moving that negative to the denominator. This would indicate go up 1 and left 2 units. So again, starting at our y-intercept, up 1, left 2, up, left, up, left, up, left. And I'm just going to continue to the edge of my graph. All right, if I connect these together, do my best to make a nice dashed line all the way across here, you're going to notice at the extremes that our graph gets closer and closer to this slant asymptote or this line. All right, so you can actually graph oblique asymptotes as long as you understand how to do division of polynomials. Now, why I decided to keep this negative 1/2 in the numerator was so that it would be easier to do this division, so that I could do a synthetic division as opposed to maybe having to pull out long division. So there's how you find the equation, how you deal with finding an oblique asymptote, and these oblique asymptotes occur whenever the degree of our denominator, in this case 1, is 1 less than the degree of the numerator. So I hope this helps out. Good luck with rational functions.